Can you hear me?
Yes, yes,
Okay.
yes.
Through the speaker, right? So let's start the second session. I'm Park Jae-woo, chair of this session, and our first speaker will be Professor John Herbert from Ohio State University, and he will talk about the fragmentation approximations for quantum chemistry. Professor Herbert, please start.
Yeah, thank you. Everyone hear me okay on Zoom? Okay, thanks. Thanks so much for the invitation. This is actually my second visit to Korea. The first one was about 10 years ago. Youngmin Ri, who's the next speaker, arranged a nice speaking tour of feels like just about everywhere in the country I went, and it was a lot of fun. So today I want to talk to you about fragmentation approximations in quantum chemistry, and specifically high fidelity approximations, where we really try to get the right answer for a very large chemical system with respect to conventional quantum chemistry run on the same system. So the idea is, roughly speaking, is we're going to take big systems and break them up into small pieces and harness the power of distributed computing to try to approximate the results of otherwise intractable quantum chemistry calculations. You can regard this, if you like, as a very crude form of local correlation, or maybe better, you can regard it as sort of a multi-scale treatment of the electronic structure problem, where we're going to potentially be using different methods at shorter versus longer length scales. And so divide the talk up into three parts. The first part will be sort of an introduction to fragment-based quantum chemistry. So most of the methods, or many of the methods, are based on so-called many-body expansion, just approximating the total energy of a supersystem in terms of monomer energies and corrections for dimers, corrections for trimers, etc. Everything that I will talk about today will be based on that traditional many-body expansion, although we have generalized this to a so-called generalized many-body expansion that allows us to tessellate a large system into overlapping pieces, and by doing that we can sort of rationalize a lot of other fragmentation methods with acronyms that you see here, and I won't talk about any of these really, but we can show how all of these different fragmentation methods can sort of be unified under a common formalism, under a common master equation, and that allows us to start thinking about comparing different fragmentation approximations. Because one point that I'll emphasize a little bit later on is that there has been really very little side-by-side comparison of different fragmentation approximations. In fact, my group has done that in 3 or 4 papers, and I really can't think of very many other papers that have tried to do that. And part of the reason for that is that most fragmentation methods are sort of done at the level of probably Python codes. Don't really matter what the language is, but within a single research group, and there's not really a common platform for comparing these approximations. And so if I'm reviewing a paper that's talking about different fragmentation approximations, I'm in sort of a curious position that if something seems a little funny, I don't really have the capability to go and do some test calculations myself and sort of try to test the veracity. And I think that's a pretty serious problem in the field that we're working on trying to overcome with a common software framework. Okay, so I mean, the advantages of this are, the advantages of fragmentation are probably fairly obvious. Relatively easy to parallelize. The storage footprint in terms of memory and disk is a fragment-sized storage footprint, and for a lot of highly correlated ab initio methods, it's really not the say end of the 7 CPU cost of CCSD parenthesis T is often not the limiting factor. It's the end of the 4 storage cost, right? And so this brings in, and even for low-level methods like DFT, if we want to think about trying to compute vibrational frequencies, even DFT vibrational frequencies come with a fairly large memory footprint as compared to DFT energies or gradients. And I would argue, and I have argued in print, that this is really the only way to get to exascale computing in quantum chemistry with relatively good parallel efficiency, where we can run on thousands of processors with near unit parallel efficiency. Now, the drawback is that a lot of the methods out there are actually relatively poor approximations to the supersystem electronic structure calculation that they're designed to approximate. To get good accuracy in the many-body expansion, you really need to go to four-body terms for a lot of systems, and the combinatorics of n-choose-4 are prohibitive. And in fact, for actual calculations that people might have done to date, the cost of the fragmentation approximation sometimes actually exceeds the cost of the calculation that you're trying to approximate. So those are the things that we'd like to address. So our goal here is to apply high-level ab initio methods to very large systems. And so I'm borrowing a plot that's sometimes attributed to John Popel, although I've never actually been able to trace it down to a Popel paper. But the idea is that we can think about ab initio quantum chemistry, different model chemistries, as points on a two-dimensional space. John used to say that we only make two approximations in quantum chemistry. One is that you use a finite basis set, and the other is that you truncate the level of electron correlation. Right? And if you can take both of those approximations to the limit, then you have exact Born-Oppenheimer quantum chemistry. And that's fine, assuming that you can treat the whole molecule at the limit along both of those axes. And so what my group is thinking about doing is adding a third axis here, where the n on this purple axis is system size. And the motivation there is that there are a number of papers over the last 10 years. I'll point you to this one by Heather Kulik when she was in Todd Martinez's group, demonstrating that QMMM calculations of thermochemical quantities, barrier heights or reaction enthalpies, are very slowly convergent with respect to the size of the QM region, so that you need to go out to 500 or 600 atoms in your QM region before the number starts changing, as you can see in these data, and that's much larger than the QM sizes that are used in practice. Right? So there's at least a need or a motivation to try to push high-level ab initio methods to be able to go out to 500-600 atoms along this third axis. Okay, and this is a proof of concept calculation showing you that we can do that for different conformations of two different proteins. This is done at a relatively low level of theory, some density functional in a double zeta basis set, and that's because we wanted to compare to the actual supersystem calculation that we were trying to approximate, and so we needed to be able to run that calculation, and so we're comparing here to DFT double zeta for these full 1200 plus atom proteins, and what you can see is that there's a full system calculation and a fragmentation calculation, and you can barely tell the difference in the energy profiles. And so we're basically fragmenting the system with kcal per mole fidelity, but with a fragmentation method that requires no single calculation that's larger than 4 amino acids for the orange fragment method here. So that's very promising, although one has to sort of ask rhetorically, do we really want DFT 631 G star energies for a large system? And I would argue, that there may be some instances where that information is useful, but in a lot of other instances, that level of theory is probably no better than a high quality force field, and the high quality force field is going to allow you to do a lot more sample. And so what I'm going to go through here is sort of my list of demands for a high fidelity fragmentation method. So there may be some reasons to want sort of cruder approximations at lower levels of theory, but this is my list of demands. And the first of them is that even though the methods I'm going to show you here today are DFT and MP2 because we're just scaling up, eventually I want to be able to do highly correlated methods in hundreds of atom systems with kcal per mole fidelity with respect to supersystem calculations. Secondly, is if we're going to go to highly correlated methods, then we're going to need large basis sets. And historically, a lot of what has been used in the fragmentation space has great difficulty dealing with extended basis sets, and especially those that contain diffuse functions. So especially methods that use some sort of electrostatic embedding charges that are determined on the fly, those things tend to become unstable in large diffuse basis sets. There's also a question of basis set superposition error, which I won't have time to talk about today, but my group has developed versions of counterpoise correction that are consistent order by order with the many-body expansion, so that's a problem that we can deal with. The third point is that I demand that gradients should be derivatives of energy, and that may seem funny to most of you to say out loud, but that's something that historically has not been the case for a lot of fragmentation methods, and I'll show you later on what some of the consequences of that are. And then the last point that we're trying to address or will address in the near future with a new software framework is this idea that historically it has not been possible for one group to reproduce the results of another group's fragmentation method, because there's a lot of details that go into these things, and they're just not available in standard codes. And I think that's sort of a problem that we're on the way to solving. We're on the way to solving it with this new code that we call PyFragment. It's a complete rewrite of a C++ code that we've been using for about 10 years. So the new Python rewrite is not yet as fully featured as the code that it replaces, but it's a lot easier to use. And so we're planning to release this, I hope, early in 2023. And I won't, for lack of time, I won't talk too much about this, except to say that right now the limitation is because of some of the way that we do the database backend, we're limited to about 60 simultaneous quantum chemistry calculations. After that, the writing to the database backs up and things become unstable, and we have some ideas about how to redesign it to get beyond that. But actually 60 simultaneous quantum chemistry processes, I think is pretty good, because that doesn't tell you anything about the hardware that can be behind those. So for things that we've been doing where the fragments are relatively small, it's kind of a sweet spot to run on about 4 cores per fragment. So that can be 60 simultaneous QChem quantum chemistry processes running on 4 processors each. And 4 is not the limit. We could run them on 8 or 12 and still probably get good parallel efficiencies. But at some point, the more hardware you request, the longer you sit in the queue of a shared computing resource. And so 4 processors per fragment, 60 quantum chemistry processes at a time, turns out to be sort of the sweet spot for us for good throughput. Your mileage will vary depending on where your hardware lives. Okay, so for the middle part of this talk, I'm going to sort of tell you what I think are some problems with existing fragmentation approaches. So the big player in this space that's been around for a long time and has been available in games for a long time is the fragment molecular orbital method. I won't tell you about the details, but if you go look up these papers, you'll often find benchmark plots like this that are showing you interaction energies for water clusters, comparing an FMO fragment approximation, either 2 bodies or 3 bodies, with the full cluster calculation. And the 3-body approach are the open symbols here. There are 3 different water cluster sizes and several water cluster sizes in 3 different basis sets. And this looks pretty good, except that all of the interesting chemical or conformational energy differences sort of all live in the little deviations between these data points. And so if you zoom in and ask how well are these calculations reproducing relative energies, the answer is not very well. So the There's two different basis sets, and the black symbols are the full cluster MP2 benchmark. And what you can see is that various fragmentation methods are sort of all over the map. And in particular, the two-body FMO, or rather the three-body FMO in green, does not seem to actually be an improvement on the two-body FMO that's in blue. And that's sort of consistent with our experience that charge embedding, which is used in FMO, can be sort of erratic. And so this is not something that we're comfortable living with. So my group has well, in particular, here's a plot of errors in a four-body approximation as a function of cluster size, comparing a bunch of different charge embedding schemes, and the green symbols are no charge embedding at all. And what you can sort of see is that the differences between different point charge embeddings are sort of small relative to the overall errors in any one of these calculations. And so in the sort of the middle part of the 2010s, my group spent a number of years sort of systematically investigating the many-body expansion and trying to figure out what was what and how well these things really work, if we're being honest. And that sort of set the stage for some of the new things that I'll get to right at the end. One thing that I want to talk about is the danger of approximate gradients. So for a couple of reasons, my group has really soured on this idea of electrostatic embedding. And one reason is the results tend to be sort of erratic. It doesn't systematically make things better. What it does do is to systematically make the gradients much harder. So if you're determining electrostatic embedding point charges on the fly using fragment wave functions, then in principle, there are response terms in your gradient. And I should say that really the only people that have done this right are the FMO people. But to take care of those terms, they have to solve couple perturbed equations. And that both makes things somewhat more expensive, significantly more complicated, and really defeats your attempt to abstract this fragmentation to say a Python layer that can live outside of your quantum chemistry code. And that maybe was really the most damning thing against trying to do it that way. Should you just try to neglect those response terms, what you rapidly find is that molecular dynamics simulations fail to conserve energy. So it's well known, even in classical molecular dynamics, that energy conservation is very sensitive to the quality of your forces. It's very sensitive to the analytic gradient really being the derivative of the energy. And so Reka, Mick Collins will tell you that the magnitude of these response terms that you're neglecting is comparable to the stopping criterion for a geometry optimization. And he's right about that. And we've looked at this for geometry optimizations, and in our hands, and apparently in Mick's hands, for geometries and frequencies, this doesn't really matter. You can sort of get away with neglecting the response terms, but for molecular dynamics, you absolutely can't. And I sort of fundamentally object to having gradients that are not derivatives of the energy. And so electrostatic embedding is sort of a non-starter from my philosophical point of view. Other things that we found about the many-body expansion are that the combinatorics of n choose 4 are really pretty awful, and they're awful enough that 3 and 4-body expansions become much more sensitive to numerical thresholds than do the supersystem quantum chemistry calculations that those things are designed to approximate. So what I'm showing you here are errors in 2, 3, or 4-body approximations to the energies for water clusters, and there's 2 sets of data in either case, one of which are basically default quantum chemistry thresholds, actually slightly tighter than QChem defaults, but and the other are very tight thresholds, and especially for the 4-body calculations, but even to some extent from the 3-body calculations, you see the loose and the tight threshold results starting to diverge as a function of system size. And that does not happen in a supersystem calculation. You can get away with pretty loose thresholds and not see that manifest as kcal per mole errors or kcal per mole differences in your final results. And this is simply a result of combinatorics. Okay, and then the last indictment kind of the previous methodology is timings. So these are RIMP2 calculations for series of water 20 clusters. And if you just compare the red, which is a traditional supersystem calculation, to the green, which is fragmentation, you discover that you're spending significantly more time computing the supersystem result. We can also do that for proteins, where these blue symbols are the cost of running, in this case, a Hartree-Fock calculation on a series of proteins, and the orange calculations are a very faithful fragmentation approximation that is also significantly more expensive. Okay, so that's the bad news, and then let's try to end this talk on a high note with what we're actually going to do about it. And so we've had a lot of success recently, just since 2020, with energy-based screening, and this is just a plot to show you an n-choose-3 curve in red, the results of a very simple distance screening procedure that anybody might imagine to try to do, but with pretty conservative thresholds to maintain kcal. And then the green symbols are energy-based screening. And so the first punchline is that this turns out to be a lot more efficient than distance-based screening. Turns out there's a lot of close range stuff that's actually negligible, that you wouldn't neglect in a simple distance-based screening, but you can neglect energy-based screening. And so the way that we started doing this is to use the effective fragment potential to sort of estimate 3 and 4 body terms, and then only those 3 and 4 body terms that EFP decides are energetically significant do we ever bother to calculate using quantum chemistry. These days we're actually using Grima's semi-empirical extended type binding models that work a little bit better and are a lot easier to incorporate into our code. The other thing that we often do is a supersystem correction at a low level of theory. So a variety of other people whose names are on the right have done this, and you can sort of rationalize this in sort of an onion type approach. The idea is we're trying to approximate a large system computed at a high level of theory by fragmenting it into a bunch of small high level calculations. But if we take a low level calculation that we can afford to apply to the entire cluster, then we can develop a correction for some of the long range induction forces that are missed by fragmentation. And so by doing that, at the RAMP2 level on a set of water 20 clusters, so this is MBE3 means 3-body expansion, and the tau means that we're using energy screening, and these are errors in kilojoules per mole. And what you see is that the energy screened 3-body expansion alone does not get us to 4 kilojoule per mole accuracy. But if we include a supersystem correction at this level of theory, Hartree-Fock, Ogg, CCPV, DZ, the gray box here is plus or minus 1 kcal per mole of the supersystem result. And you might say to yourself, well, okay, but you have to do this level of theory, but actually in comparison to the end of the 5 cost of MP2, the limited number of 3-body MP2 terms that we have to do is actually about the same cost as the supersystem Hartree-Fock, and the total cost of that composite calculation is shown in the blue symbols. And I don't have data to show you, but we've started to do some experimentation about, can we get away, instead of using Hartree-Fock augmented CCPV-DZ, can we do Hartree-Fock 631G star? We haven't quite gotten it to kcal per mole levels of errors, but we're getting close. And that's pretty encouraging, because if you have a quantum chemistry code that can deal with compound SP shells, 631G star is about 15 times faster than CCPV-DZ. Okay, and then the last thing before I wrap up is to say that we've now extended this to the 4-body level. So everything actually from this point on in the talk is unpublished. But by means of energy screening, we're actually able to do 4-body expansions in large systems for the first time. So this plot shows you how energy screening allows us to cull a number of terms. So as we tighten the energy screening threshold or increase the energy screening threshold, we gradually cull the number of four-body terms. The errors then, as a function of that threshold, are shown here. So these are a bunch of different isomers of water 20, and the idea is that we can relax that threshold all the way up to about 0.1 kcal per mole, and we still stay within this sub kcal per mole accuracy window. That's nice in an absolute sense. However, it has been suggested that for dynamics, it suffices to stay within an error of about 0.1 kcal per mole per monomer, because that's 10% of KT per monomer at room temperature. And so if 0.1 kcal per mole per monomer is your target, then we can relax that threshold all the way to almost 1 kcal per mole, and we're only picking up maybe 3,000 four-body terms out of a total of 635,000. And so we've culled, I can't even calculate in my head what the percentage of the four-body terms that we've been able to throw away, but I'll tell you that the largest complete four-body calculations in the literature so far are in water 21. This is water 64, which we like a lot because 64 waters in a periodic simulation cell is a not embarrassingly small liquid water calculation. Okay, and then the last thing before I wrap up is to say we're doing enzyme thermochemistry now, and so this is the Heather Kulik protein from the beginning of the talk. 35 fragments in our model system. 14 of them have charged side chains, although the total charge is only -1, and that turns out to be interesting. So we can converge a three-body calculation of either the activation energy, the barrier height, or the reaction enthalpy, but only if we carry out the calculation under low dielectric boundary conditions. And so it turns out, perhaps not surprisingly in hindsight, although I haven't seen this in the literature, that if you're running this large 600 atom model of a protein in the gas phase, that's not a good benchmark for your fragmentation method, because in those charged side chains with vacuum boundary conditions, the charges really don't know where to go. You've got a carboxylate group exposed to vacuum. That charge doesn't really know where to go, and you don't have a well-defined target for your many-body expansion. And so you need to put this in dielectric boundary conditions. These are actually only dielectric boundary conditions of epsilon equals 4. So even low dielectric boundary conditions at least gives you a well-defined target. Okay, and so that's the end. And so I'm just going to put this up here and let you read the conclusions and open the floor to questions. Thank you.
Okay, so we have some time for one or two questions.
Yeah, very nice presentation. Just for curiosity, so let's say if I have a long chain system, activation fragmentation works very well because the ends don't interact anyway. But if I have a very crowded system, then it might be more difficult. How does this come into the picture?
Well, so I mean, here our active site is certainly three-dimensional and compact, right? And so you know, you pick up a relatively large number of fragments that way. And actually the protein problem is interesting. We thought about this a lot years ago in the context of counterpoise corrections, that I think Tanja van Morik has a couple of papers from maybe 10 or 15 years ago showing that basis set superposition error can artificially skew your protein folding landscape, because if you have a compact structure, you have more neighbors to borrow basis functions from as compared to an extended structure. And so we thought about that very carefully to try to make sure that our fragmentation approximations were giving us a consistent error across potential energy surfaces. And so in the compact structure, you certainly get more fragments and you get more energetically significant fragments, but we pick that up in an automated way.
Eric?
Is that just enough to get over or
Uh, I don't know. The short answer is properties are certainly harder. We and Daniel have played around with optical rotation spectra. I mean, he did it first and published a paper showing that it didn't work, and we tried to do better and never published that for a reason, because we never got anything better than your doesn't work. So that's an open question. I think some properties are probably harder than others. If I had to guess, static polarizabilities are probably doable. That might have been in your paper. It's been a long time since I read it, but yeah, but other things are certainly going to be harder.
Okay, the last question.
So you talk about gradients in sort of proper relative of the energy. So I'm curious. So when you do this energy embedding, right? So do you get the energy and gradient continuous function of the
You need to use a switching function in energy space in the same way that you would in a classical MD, you would cut off the van der Waals interactions with a smooth cutoff, but that can be a smooth cutoff in energy rather than distance, and then you get it right.
Right, let's thank Professor Herbert